Before we talk about power series, I would like to do one example of series convergence. So let's assume that there's a sequence C sub k and that the limit of C sub k plus 1 over C sub k in absolute values is equal to k. So the limit of the ratio of the terms as k goes to infinity is equal to capital K. Then the question we want to ask is, for what values of x does C sub k times x minus a to the k, that sum from k equals 0 to infinity, converge? The way that we can find the values of x for which this series converges is to use the ratio test. So let's look at the limit as k goes to infinity of the absolute value of C sub k times x minus a to the k plus 1. So this is actually C sub k plus 1 divided by C sub k times x minus a to the k power. Well, then note that x minus a to the k plus 1 over x minus a to the k is just going to be x minus a. And so we're going to take that in absolute values and we're going to take it outside of the limit because that does not depend on k. And what is left is the limit as k goes to infinity of C sub k plus 1 over C sub k. So in fact, what we're left with is that limit, which is equal to capital K times x minus a. And then by the ratio test, this converges if k times the absolute value of x minus a is less than 1. So we can say that this converges if x minus a in absolute value is less than 1 over k. So by the ratio test, we have that this converges if x minus a is less than 1 over k, and then it diverges if x minus a is greater than 1 over k. Now, if x minus a in absolute value is equal to 1 over k, then for my ratio test, we will have that k times x minus a would be equal to 1. And so we would not be able to use the ratio test to determine convergence or divergence. Now let's move on to the definition of a power series. A power series is any series of the form sum from k equals 0 to infinity of C sub k times x minus a to the k is actually called a power series. And if we define a function f of x equal to that infinite sum, that power series, then the domain of that function, f of x, is the set of all x for which the series converges. Now, we just saw in our previous example that there is a set of x for which the series converges, and then that's going to be the domain of our function. Remember that a domain is the set of allowable inputs to our function f of x, and we're saying in this case, the domain is the set of all x's for which we get a convergent series, which then would give us a value for f of x. Now I'm going to define what's called the radius of convergence. The radius of convergence of this power series is the positive number r such that the series converges for all x minus a less than r in absolute value and diverges for all x minus a greater than r in absolute value. And we saw that we were able to determine a radius of convergence in our previous example. This is called a radius of convergence because what we like to think about here is we like to think about there being a point here A on the number line, and then we can move out a distance r from A here and negative r. And then the interval, absolute value of x minus a less than r, is actually this open interval right there. And we say that we have convergence within that open interval and divergence outside of that interval. Really quickly, that's actually a minus r and a plus r. So the distance here is going to be r, and the distance here is going to be a minus r. So within the interval a minus r to a plus r, the series will converge, and then outside of that interval, it will diverge. So here we're calling r our radius of convergence. Now, there are three cases that can occur when we're looking at computing the radius of convergence. Okay, so we're going to let a sub k be our terms in the sequence. And if the ratio of our terms is equal to 0, okay, then what's happening by the ratio test is that we have that the limit as k goes to infinity of a sub k plus 1 over a sub k is equal to 0, but that's always less than 1. And so we call our radius of convergence here infinity, and that is because x can be any real number, and the ratio test will tell us that that series converges. Now, if the limit as k goes to infinity of the terms is equal to infinity, then here, in this case, the limit of the ratio of the terms is equal to infinity, and that's always going to be bigger than 1. And so we say that the radius of convergence here is 0. Now, it may be strange that we're calling the radius of convergence 0. You would think that this series doesn't converge for any x, but it actually still converges for x equals a. Because if we plug in a to our series, then a minus a is 0, and we get the sum of zeros, an infinite sum of zeros, which does converge. So there's still one point at which it converges. Now, the third case that we get is that our limit as k goes to infinity of our ratio of terms is equal to k times x minus a. And that's actually what we had gotten in our previous example. We saw that the limit as k goes to infinity of our terms a k plus 1 over a sub k was equal to k times x minus a, an absolute value, and that had to be less than 1. And so we saw that the radius of convergence then was 1 over k, because x minus a, an absolute value, had to be less than 1 over k. So in this case, our radius of convergence is actually going to be 1 over k. So these are the three possibilities for our radius of convergence. So let's look at an example. So we want to find the radius of convergence for our series, and our series is going to be 3x plus 5x squared over 2 plus 7x cubed over 3 plus 9x to the fourth over 4, etc., etc. So first, we just need to write out what this series looks like. So this is going to be the sum from k equals, let's go with 1 to infinity. And we're going to notice that the denominators go 1, 2, 3, 4, 5. So this is going to be divided by k. We're going to take x to the k power. So we can think about this as being x minus 0 to the k power. And then what we have are odd terms, 3, 5, 7, 9. So these actually start as 2k plus 1. Now, we're going to do the ratio test. So we're going to take the limit as k goes to infinity of the ratio of the terms. So in this case, it's going to be 2 times k plus 1 over k plus 1, x to the k plus 1. And then we're going to divide that by 2k plus 1 over k, x to the k. Now, x to the k plus 1 over x to the k, that's going to give us just x, and we're going to put that in absolute value and bring it outside the limit because, again, it does not depend on k. So we're left with k going to infinity of, our numerator here becomes actually 2k plus 3 over k plus 1. And then we're going to multiply by the reciprocal of the denominator, so that's going to be k over 2k plus 1. So finally, we will have the absolute value of x. And then if we look at this limit, well, 2k plus 3 over 2k plus 1, as k goes to infinity, that's going to give us 1. And then k over k plus 1, as k goes to infinity, that's going to give us 1. So this whole thing, the limit is going to actually just be 1. So we get absolute value of x times 1. And then by the ratio test, we want it to be less than 1 for convergence. Okay, so we have a radius of convergence. Which is r equal to 1. And that says that the series converges for absolute value of x less than 1, and then it diverges for absolute value of x greater than 1.